such a file system, and later you can audit the entire history of this file system. But you can do that as long as the file stays in that file system, or maybe transferred to yet another standard or other trusted file system. We cannot carry this integrity verification properties across systems. As we exchange this document between or among a lot of different users, we cannot pass on this integrity preservation properties. And then there's this nice work by Mary Baker in 2002, which showed that how you can prevent systems that are member of a distributed system, how you can prevent them from cheating or lying about their own states. What they do is to entangle their own states with each other so that no one can lie. If someone lies, the other party can serve as a witness and catch the liar. But again, we are talking about mobile data that gets passed around. And finally, there's this famous work on secure audit logs by Schneier and Kelsey, where they have a model of securing the audit log so that they have a trusted notary who notarizes the audit logs periodically, or start with a hash chain seed and periodically recreate the keys, and so that an adversary can come in and they can generate fake future logs, but they cannot change things that happened in the past. But here our problem are different. Our problem is that the real owner of the document, the real person who signed the document initially, the insider can be the adversary. We're not talking about an outside adversary. We are also focusing on logs on a much finer granularity. Not like a single log for the entire system, but sticky logs for each file that get passed along with a file. So in this backdrop, we present our solution for securing data provenance. In our model, we assume that provenance is in the form of a chain. Each entry in a provenance chain contains the actions or record of actions by a user. And each provenance record has this schema. We have the user component, which contains the identity of the principal. Then we have the work log, that is, we have a field where we store whatever action was done or taken by this user in this to modify the document. And then we have some other entries, for example, the confidentiality log. I'll explain each of these fields in the next few slides. We have confidentiality logs field for decrypting the encrypted modification log. And finally, we have integrity checksums for protecting the integrity of the chain. Now, recall that our goal in confidentiality is this. Each user trusts a subset of the auditors, and our goal is that only the trusted auditors, the auditors that are trusted by the user, should be able to see the user's actions on the document. So how do we do that? If there was a single auditor, then the solution would be straightforward. We'll just take the modification log and encrypt it with the auditor's key, and we have this encrypted modification log. We include it in the provenance entry. So later the auditor can come in and use his key to decrypt this, see what happened there. But now we're talking about multiple auditors. So we can use an extension of the same idea. We can take the modification log, make multiple copies, and encrypt each copy with a key of a trusted auditor. And then we end up with these multiple encrypted modification logs. We include all of this in the provenance entry. So each trusted auditor who can decrypt one of these logs can see what happened. But here we are wasting a lot of space. We are including a bunch of copies of the same thing. So our solution is to encrypt the modification log with a randomly generated key, session key, and then take the session key and encrypt the key only with the keys of the trusted auditors, copies of the session key with the keys of the trusted auditors. So now we have this encrypted modification log and these encrypted keys. So each auditor who can decrypt a key can now read the modification log. We can also optimize further. If there are, say, 100 auditors and you trust 60 of them, does it mean we have to include 60 copies of the encrypted key? Well, no, we can use different optimization like the broadcast encryption tree to reduce the number of keys you need to encrypt things. I'll just skip over this slide because we are running a little bit late. So the idea of broadcast encryption is that you arrange the auditors in the leaves of a tree, and each auditor knows all the keys all the way to the root. So if you trust everyone, then you encrypt with this key. If you trust just D, then you encrypt with D's key. And then if you trust B and C, then you use these two keys, their two keys. But if you trust A, C, and D, then for A you use this key, and for C and D you can only use this key to encrypt it. So at the end of the day, for n auditors, you need log n of keys to be included in the chain. So here's again a recap of our solution for confidentiality. We stored the encrypted modification log in this W entry. We also throw in the hash of the document so that we can keep a mapping or binding from this provenance entry to that particular version of the document. And we then encrypt this random or session key with the keys of the trusted auditors and put them in this keylog entry. Next, we look into how we can protect integrity. Here our goal is that no one should be able to insert things to the history or remove things and so on. So the solution is straightforward. We take, suppose we are trying to compute this new checksum. What we do here is to take the new provenance entry, hash it, then concatenate it with the old checksum here, and then sign it. So this is the new entry, we hash it, concatenate with the previous checksum, and then sign it with the key of the current user. So that way, this forms a signed hash chain, so that now no one can remove things from the middle of the chain, because the subsequent checksums will not match. No one cannot also tamper any entries in the chain, because now we use the content of an entry to create these checksums. So if you tamper something, then you can't, the checksums won't match. Next, finally, we look into confidentiality, fine-grained control over confidentiality. So what I mean is, sometimes you have classified documents that you are supposed to release to public, and these classified documents have secret parts, like this, the parts we indicate here in red. And one way to declassify or release is to redact or remove the sensitive information. You just remove it, or you delete it with black ink and then release to public. But the problem is, what should we do with the provenance chain? If we release the provenance chain as it is, the provenance chain itself might contain secret entries. Now, by looking at the provenance chain, it might be possible for the people, for the outsiders to see the sensitive information. But if we redact these sensitive parts from the provenance chain, we break the integrity checksums. Because now no one can verify the integrity of the chain, because you have modified parts of the provenance chain. So to solve that problem, what we do is to use cryptographic commitments. Now a commitment is just you hash with a random key. You hash, concatenate with a random number and then hash it, and that's a commitment of that original value. So we use it in this way. When we are creating a provenance, new provenance entry, there might be some non-sensitive information indicated here in blue, and then sensitive information indicated here in red. When we are creating the provenance entry, we add this commitment. We take a commitment of the sensitive information and store it alongside everything. As long as it stays inside your organization, it's fine, you keep everything. But also, when we are computing the signature, computing the checksum, we use the non-sensitive portions, and instead of the sensitive portions, we use the commitment. So now we have made it disclosable. Now we make it possible to disclose this provenance entry to outside. When we want to disclose it to the outside parties, we just throw away the sensitive portions. But in the checksum calculations, we did not use the sensitive portions. Rather, we use the commitment of the sensitive portions, which we include here. So now anyone who receives it won't see the sensitive parts, but yet they will be able to check the integrity of the provenance chain. And finally, we have some schemes for summarizing provenance chains. What do we mean by summarize? Sometimes provenance chains can grow really large. Suppose you have a file, small file, say 100 kilobytes, but it's edited frequently.